In this class, we're going to consider the power rule for differentiating. So generally, the power rule is the first rule, the first technique you'll learn for finding the derivative of a certain type of function for polynomial functions. There are different techniques for finding the derivative for different function types. So if you've got a trig function or a composite function or different families of functions, they've all got their own differentiation techniques. So we're going to look at this first set of techniques which apply to polynomial functions, and we're going to consider first of all functions in the form f of x equals ax to the power of n. So when we come to take the derivative, there's a couple of things we need to consider. The first is whether the function is differentiable. That means, is it in a format that looks like this? And I'm going to show you examples in a moment where it's not. And in those cases, we need to manipulate the function first of all to get it into this format. So the power rule, which we're going to look at today, only applies to functions that are in this format, and sometimes you've got to manipulate them to get them into that format. The next thing we need to consider is the notation. So when we take a function like this and we notate its derivative, we write it as either f prime of x or f dash x. It depends really where you live. If you're in the UK like I am, then we call it f dash x, but occasionally f prime x. If you're in the US or somewhere else, you probably call it f prime of x. Whatever you call it, the notation itself is the same, and we call that the derivative. And the power rule says that you multiply by the power, so that's kind of why it's called the power rule. You multiply by the power and you reduce the power by 1. Now this formula looks a little confusing. Remember that in reality a and n are likely to be numbers, so it's actually easier to use when you've got a real example. So that is a great mantra to get down. Multiply by the power, reduce the power by 1, rather than thinking in terms of the formula. You'll probably never really use that formula as such. You'll just learn how to multiply by the power and take 1 off the power. So we'll look at an example of that in a moment, but just before we get there, there's an added complication with the notation, because sometimes you've got functions that are notated using y instead of f of x. So when calculus and differentiation was developed, like hundreds of years ago, two guys were working on it separately and they came up with different ways of thinking about it. The rules are the same, but we've ended up basically with two different notations. So they mean the same thing, the derivative is still the same thing, but when you've got a y function, we write the derivative as dy dx. And the further you get into calculus and differentiation, you'll start to maybe break this down and think about what it means, and you'll maybe start to break that down and think about what it means and how we get from here to here. When you take the derivative in this notation, it's just the same. So multiply by the power, so multiply the n in front, and then reduce the power by 1. So you get the same formula both ways. Okay, so that sets up what we're going to do. Let's go ahead and look at some examples to kind of bring this to life. So let's just take something that matches this format first of all. So let's go for f of x equals 3x to the power of 4. So we're just going to multiply by the power and reduce the power by 1. So we multiply the 4 in front, but the 4 will times to the 3. So this na here, remember, if they're numbers, we wouldn't just write them next to each other like 3, 4. We just go ahead and multiply them. So 3 times 4 is 12, so we get 12x. We take 1 off the 4, we reduce the power by 1. So using the power rule, we've got 12x cubed. The functions that fall into this category though, they sometimes have more than one term. In fact, usually they'll have more than one term. So it doesn't have to be just like ax to the n. It can be something like this, where you've effectively got a polynomial, say 2x to the power of 5, and then some more terms. You could, for example, also have, like, say, a negative power, something like that. It doesn't matter if the power is positive or negative, you just do the same thing. So the derivative f dash x will equal 10x to the power of 4, using the power rule. Minus 4 times 3 is minus 12, x to the minus 5, because we're taking 1 off of that power. Okay, right, so let's have a look at maybe one more example here and then some different cases over here. Let's make this one a y function. So let's say we've got minus 3x to the minus 2, and then let's say we've got just a number, a constant on the end. I should have said over here, when you've got a y function, sometimes you'll see the derivative notated y dash like that. That's more of an informal, just like a casual way of doing it. But it does mean the derivative as well. And it's unusual. You probably won't see that in textbooks, but your teacher might, when writing on a board real quick, just go y dash to save writing dy dx. Okay, so got our y function. We're going to make our derivative dy dx. So just the same thing for the first term, multiply the powers together, which is going to give you a positive 6 because you've got a double negative. X, reduce the power by 1 down to minus 3. Constants differentiate to 0. So if you've got just a number, the derivative of that is 0. One way you can think about that is because you could write this as 7x to the power of 0, because x to the 0 is 1, 7 times 1 is 7, so that would just be another way of writing the number 7. But if we apply the power rule to this and we multiply by the power, so multiply by 0 makes it 0, so we would just get a plus 0 on the end, which we don't bother to write. So try to remember that a constant, a number, which you'll see a lot of, will just disappear in the derivative. This looks a little ugly. This was meant to be a 3. Okay, cool. Right, so let's maybe define some functions which are not in a differentiable form. Functions, by the way, usually use an f, but they don't have to use an f. As you move into real-world context type questions, these will start to represent, whatever they represent in the real world, like time or pressure or volume or speed or something like that. So the letters will probably start to change. I'm going to call this one g, just for a bit of variety. So let's say that our g function is a fraction, like 2 over x cubed. So that fraction there obviously is not in the correct format, but we can manipulate it using the rules for exponents, the rules for indices, to make it into 2x to the minus 3, just by bringing the x cubed term to the top. That's now in the correct format, ax to the n, so we can go ahead and take our derivative. So g dash x, which would be minus 6x to the minus 4. Okay, so that's how we would deal with that situation. Another common situation, I'll go back to an f function. Another common scenario is where you've got some kind of root. So let's say we've got like a square root. Yeah, that should be fine, square root of x. So again, obviously not matching up with this form. I mean, there's no square root up here. So we've got to consider, how do we deal with this? Well, again, using a rule for indices or for radicals, surds, you could change that to an x to the 1/2 power, because a 1/2 power and a square root are the same thing. This is now in the correct format. Doesn't matter that that's a fraction. The n value is allowed to be a fraction. So taking our derivative just in the same way, multiply by the power, which will be 1/2 x to the minus 1/2, because taking 1 off of a half gives you negative 1/2. These are just a handful of the huge variety of types of scenario that you're going to be asked to differentiate. It will take a little bit of experience to learn how to deal with different situations. You might see a combination of something like this and this. You might see much longer polynomial expressions. But when it comes down to it, once you've got them in the correct format, your power rule is still going to just follow this rule here. Multiply by the power, reduce the power by 1. Just say that over and over again, like a million times, and you should remember it. But that is the introduction really to the power rule, because you'll use it so often and there's so many different varieties of question types that will require power rule differentiation that it'll just be a case of learning the rule and then trying to adapt it to the different scenarios that you encounter. If this is brand new to you, then I would definitely recommend working quite a few practice questions. You want to get really good with this technique to the point where you just don't really think about it. You just go ahead and write down the answer.